So today we're going to take the work that we've done with frequency tables, um, which we just haven't called them that, and conditional probability, and just kind of put it all together. So what I want you guys to do is, we're going to skip that warm up for right now. I want you to turn to page 63 on your books. This is just the warm up for the day. You actually might want to pause the video and see if you can do it. It's just kind of a logic type thing. And then come back, obviously hit play and check your answers with me on the video. So it says Kira likes number puzzles and is tackling the puzzle below. The puzzle is incomplete. When it is complete, each total at the end of a row will be the sum of the numbers in that row, and each total at the end of the column will be the sum of the numbers in that column. So this should look familiar to you because this is when we started doing independent and dependent. We started looking at data and tables. So if you look, we know every column needs to total, every row needs to total. So I would just start here and say, okay, 10 plus something plus 10 is 25. So 10 and 10 is 20. I need 5 more to get to 25, so therefore I know 5 goes here. Then the next total that I can work with, here we have now 5, something, and 8, so 5 plus x plus 8 should get me to 30. Well, 5 and 8 is 13, and I need 17 more, so if I add those together, I get to the 30 on the right-hand side. Okay, then I would just start piecing it together. If you go down to the bottom row, 10 plus something, we have too many unknowns. Same thing here, we have too many unknowns for this column. The totals column, though, should total to 100, so we can do the bottom total and the top total. So 30 plus 34 is 64, which means there's 36 left, so that these three total to 100. And then 25 plus 40 is 65, which means we need 35 more to also get to 100, because remember, these get me to 100, as do those get me to 100. So then 12 plus 8 is going to get me to 20. I'm going to need 15 more to get to the total of 35 here. And now these I can do based upon their rows. 10 plus 12 is 22. I need 14 more to get to 36. And then you could do this based off of column or row. 10 plus 15 is 25. I need 9 more to get to 34. You could also say 14 and 11, or I'm sorry, 14 and 17 is 31, so I need 9 more to get to 40. Okay, so we're just going to kind of manipulate that type of data today and then bring in conditional probability as well. So if you look at page 65, unfortunately, they gave you all of the data on page 65, and then we're going to manipulate it on page 66, which is a little annoying, but whatever. So the student council wants to host a school-wide activity. Council members survey 40 students, asking them to choose either a field trip, a dance, or a talent show. The table below shows the survey results with the surveyed students numbered 1 through 40. So if you notice, I just put a red line down here because it's all the data. They just put it into 2 columns. You don't read it all the way across. So student number 1 is a 10th grader, and they preferred field trip. Student number 2 is a 12th grader. They preferred the dance, etc., etc. Okay, and through 40. So what they're asking us to do, I'm going to do 2 pages at once here. Sorry, I know that some of this is cut off, but you can see the important stuff in the data table. All right, so they want us to set up a tally table. All that means, you guys, is you're taking all of this data and figuring out what the numbers are. So the 2 things that we're focusing on are what they liked, so their activity, and then their grade. Okay, so it doesn't really matter which way you set these up. I'm going to put their grade here, so they could be a 10th grader, an 11th grader, or a 12th grader if you look at the data. And then across the top, I'll put what activity they liked. So in this case, that is the talent show. So TS for the talent show. There's a little key at the bottom down here. FT for the field trip, and D for the dance. So literally, when it says set up a tally table, and this is pretty redundant, we're not going to really ask you to do this, but this is where this all comes from. It's just taking the data and saying, okay, student number 1 is a 10th grader who liked the field trip, so we're going to put a tally for that student. Student number 2 is a 12th grader who liked the dance. Okay, 12th grader who liked the dance. Student number 3 is a 10th grader who liked the talent show. So it's just a way to organize your data. If you go through and do that for every single student, you should end up with 4 tally marks of 10th graders who like the talent show, 5 of 11th graders who like the talent show, and 3 of the 12th graders. And then in the field trip category, you would end up with 8 who liked the field trip, 3 11th graders who liked the field trip, 1 12th grader. And then the dance is 2 10th graders, 6 11th graders, and 9 12th graders who liked the dance. So basically just going through, and it's a way to organize your data. I essentially just did that for you. You don't need to go through and do that one by one. So number 2 says tally the data. Okay, well, we just did number 2, right? Setting up the tally table is what's in purple. What's in blue is tallying the data. So then it was, when it says create a two-way frequency table, all you're doing is formalizing what you have here. So I can go back to single page because I don't need that data anymore. And you're just saying, okay, I said this was my grade. I said this was the activity they liked. So this is 10th, 11th, and 12th grade. And then this is the talent show. This is the field trip. And this is the dance. So all you're doing is saying, okay, look at your talent. Okay, this is 4. This is 8. So you're just counting up your tallies. This is 2. And then go from there. So 5, 2, 3, 1, 6, and 9. So that's what you should come up with if you counted your tallies. Okay. This is what you're going to be given, is this actual information about something, and then we're going to do something with it. But example 1 is just showing you where it came from. Okay. So kind of redundant, hopefully a little bit kind of like, duh, we get it on this. If you turn the page to page 67, you'll see that example number 2 has a completed two-way frequency table. So it just means it's comparing 2 things. And if you notice, it looks oddly familiar because it's a frequency table that we literally just made in the last example. So now it says, consider the following events that apply to a random student who participated in the survey. So when you see 10, it means they're in the 10th grade, 12, they're in the 12th grade, field trip, FT, and TS is talent show. So it says we're comparing 2 things. We're comparing the probability that you pick a 10th grader out of the sample space of the field trip. So the probability I get a 10th grader knowing that they liked the field trip. And then the probability that I get somebody who liked the field trip out of the sample space of the 10th graders. So you guys, you don't need the formula here. I'm just going to go back up to my two-way frequency table and say, okay, 4 plus 5, I'm going to do my totals. So 11 people total liked the talent show. 12 people total liked the field trip. And 17 people total liked the dance. And then across the board, 4 plus 8 plus 2, there were 14 10th graders that were surveyed. 5 plus 3 plus 6, there were 14 11th graders that were surveyed. And 2 plus 1 plus 9 is 12. So if you add those up, 14 and 14 and 12, add those up, you get 40. 11, 12, and 17, add those up, you get 40, which is awesome, right? We want that to match. And the better news is the very first example had 40 students in it, so we did our data correctly. So if you look at this first one, compare the probability of a 10th grader in the that liked the field trip. Remember, this is now your sample space. So out of all of the people that were surveyed, my sample space of field trip is 12. And out of those 12 students, how many in that sample space were 10th graders? 8. So that means that is 2/3 or 66.67%. So the probability of getting a 10th grader out of all of the students who picked field trip is 66.67%. Now, if we do it the opposite way, we're changing our sample space. Now we're saying out of all the 10th graders, what's the probability that they liked the field trip? So my 10th graders, well, I had 14 10th graders from up over here. Out of those 14 10th graders, how many of them liked the field trip? 8 of them did. Okay, so 8 out of 14 reduces to 4 out of 7. So we have a 2/3 chance on one, a 4/7 chance on the other, which is a 57.14% chance, which means it's more likely that out of the people who liked the field trip, that you will get a 10th grader. Okay, remember your wording you have to be really careful with here. Now, the last question they're asking are they independent? So we're just going to go back to our independence formula. So the probability of a 10th grader and the field trip equals the probability of a 10th grader times the probability of the field trip. Well, the probability of a 10th grader and the field trip, let's see, how many 10th graders and field trip? 10th graders and field trip is 8 out of 40. The probability of a 10th grader is 14 out of 40. And the probability of a field trip is 12 out of 40. So we get 0.2 equals, if you multiply that other side out, you get 0.105. So remember, you guys, if you're not very good with the decimals, you're looking at something that says 20% equals 10.5%. So no, they're not independent. They're definitely dependent because they're not equal. Okay, which makes sense because if you look out of the people in the field trip, it was very heavily weighted that the 10th graders liked the field trip compared to the 11th graders or the 12th graders. So it makes sense because your data is a little skewed, so it makes sense for them to be dependent. Okay, so the next question is doing the same thing. I'm interpreting the results as we go, so we don't need to do that. So it might be good for you to sit and pause the video and work out this next question and then hit play again and see how you do. So here, my sample space is going to be people who liked the talent show, which was 11 people total. Out of those 11, how many of them were 12th graders? Well, 2. Okay. For the next one, the probability of picking somebody who liked the talent show knowing it was a 12th grader, well, we have 12 12th graders, so that's my sample space. Out of those 12 12th graders, 2 of them liked the talent show. Okay, so it looks close, but remember you're pulling a 2 from 2 different areas, so, or you're talking about 2 different things. So 2 out of 11 is the probability that out of the talent show people, 12 of, or you will get a 12th grader, excuse me. And the second one is out of all the 12th graders, that's a probability that you're going to get somebody who liked the talent show. So here, this is 0.1818 or 18.18%. This right here is 1/6 or 0.1667, so 16.67%. So while it's close, it's more likely that out of the talent show people, so the people who liked, I'm just shortening this, liked the talent show, you will pick a 12th grader. Okay, it's pretty close, but your sample space on the first one is just a tiny bit smaller by one person, so it's going to be more likely. Now, when we compare them and interpret the results, oh, I'm sorry, we just did that. When we talk about independence, we're looking at the probability of a 12th grader and the talent show equals the probability, I'm just going to shorten this to 12, times the probability of the talent show. So, the probability of a 12th grader and the talent show is 2 out of 40. The probability of liking the probability of getting a 12th grader is 12 out of 40. And the probability of getting somebody who liked the talent show is 11 out of 40. So we end up with 0.05 equals 0.0825. So that's a 5% and an 8.25%. So again, we're looking for a 1% swing. Now, that's pretty close, but they are still dependent on each other. Okay. They are not independent. So in this case, if you notice, the numbers of 12th graders that like the talent show were pretty low. So the probability of getting a 12th grader and the talent show is dependent on each other. Okay. All right. So the last one, example number 3, we're kind of going through the same thing. So if you, again, want to pause it and read through it and see how you're doing. So you guys, this isn't like a huge, I'm sure you've noticed, this isn't like, oh my God, all this new stuff. We're just putting it all together and using a different way of supporting the data than we have before. Okay. So for example number 3, it says a cafeteria manager recorded the choices of 100 students who chose one food item and one beverage. All right, so the first thing I'm going to do when I see one of these tables is total it up. 34 and 26 is 60. 24 and 16 is 40. We know they should add up to 100, which they do. 24 and 34 is 58. And 26 and 16 is 42. If you add those together, you get 100. Okay, so when you see M, it's talking about milk. When you see B, it's talking about a burger. And when you see P, it's talking about pizza. Right, so, all right, first probability. The probability that a student selects milk knowing that they selected a burger. So remember, your sample space is the second one. So 58 people chose a burger. That's what I totaled up there. Out of those 58, 34 wanted milk. So 34 divided by 58 is 0.5862, so about 58.62%. So the probability of selecting a student who wanted milk knowing that they got a burger is 58.62%. So then now reverse that. The probability of a student ordering a burger knowing they got milk, well, my sample space is the 60 students who got milk. Out of those 60, 34 ordered a burger. So 34 divided by 60 is 0.567. Sorry, it's a little off. Just sticking with our 4 decimal places. So 56.67. So those are pretty darn close, but don't let that get you caught up on necessarily independence. So 58.62 and 56.67. So are they independent? So the probability of milk and a burger is the probability of milk times the probability of a burger. So milk and a burger is these 34 out of the total 100. The probability of just milk is 60 out of 100. And the probability of just a burger is 58 out of 100. So if you go through and we get obviously 0.34. I can't believe I just put that in my calculator. That's cool though. 60 divided by 100, we know what that is, but then we're going to multiply that by 58 divided by 100, and we get 0.348. All right, so we're looking at 34% even equals 34.8% even. That is close. That is within a percent. So these are actually independent of each other, okay? Which kind of makes sense because if you notice how really close your conditionals were when you did them separately, the probability of getting a student who chose milk out of the people who got a burger and then vice versa, it was pretty darn equal. So yeah, they're independent, which means there isn't necessarily a connection between ordering a milk and ordering a burger. Okay. All right. So, because if you look, your sample spaces for those are really darn close, 58 and 60. All right. So, let's go back here. Okay, so now we're talking about pizza. So, we're going to do the same thing with pizza. Here, my sample space is the probability of ordering milk knowing you got pizza. Let's see. So, pizza is 42 kids. And of those 42, 26 got milk. So 26 divided by 42 gets me 0.6190, so 61.9%. And then if I do the other side, now my sample space is those who got milk, which is 58. Of those 58, 24 ordered pizza, which is 0.4138, so 41.38%. So, to check for their independence, we have the probability of milk and pizza is the probability of milk times the probability of pizza. So, milk and pizza is 26 out of 100. The probability of milk is 60 out of 100. And the probability of pizza is 42 out of 100. So we want to calculate those. We know this is going to be 0.26. When we multiply the other two together, we get 0.252. So we're looking at 26% and 25.2%. So again, I would say that these are also independent. Okay, so ordering milk doesn't necessarily mean you're going to order pizza and vice versa. So if you look, the numbers are pretty darn close here, which makes sense. So interpret the results. This is just your more likely. So down here, well, close. It is more likely to pick someone who wanted milk out of the students who ordered a burger. And then for the second one, it is more likely to choose, which one was more likely? A student who selected milk from the group who ordered pizza. Okay, so if we look back at the data, here, sorry, I wrote that fast and then kept going. It's just analyzing it and interpreting it. And if you look, more students, so notice both of these, it's more likely to pick somebody who got milk, whether you're looking at the group who got the burger or who ordered pizza. Well, if you look at the data, that makes sense because 60 people ordered milk compared to 40. So it makes sense, you know, more people are ordering milk. So that doesn't surprise me. It's not saying that it's going to happen. It makes sense. Okay. So your homework tonight is page 71 to 73, number 1 through 10. And check your answers in the back. Remember, the book checks for the book uses conditional probability to check for independence. We're just sticking with our straight, the probability of A and B equals the probability of A times the probability of B. So just use that. So it might look funny in the back of the book. Just look for the independent or dependent.